especially the stable boundary layer. So why don't we go ahead and get started. Also, if you have any questions, I would ask that you post them in the chat and I'll get to them at the end of the talk. I'm not able to see the screen or anything right now. I have just my PowerPoint open. So it's probably no stranger to any of y'all who may have seen any of my talks up till now that the technology of uncrewed aircraft systems or UASs is really revolutionary in its ability to fill the atmospheric data gap left behind by routine operational observations in the boundary layer. This is because these UASs can sample the same thing that traditional radiosondes can: pressure, temperature, humidity, and winds. This is an example of the CopterSonde UAS built by CAS and now CIRO engineer Tony Segales, which was characterized in his 2020 paper. And in a 2020 study by Tyler Bell et al., we actually were able to show that these observations were very similar and very comparable to radiosondes and ground-based Doppler lidar for all of these parameters measured. So it's great that we have all of these observations. And if you really break down what a UAS is actually seeing while it's ascending through the atmosphere. So let's say we have this rotary wing UAS, just a little quadcopter. It ascends through the atmosphere while continually sampling. That produces a time series of data, for this example being temperature. And when we're post-processing, we discretize this into chunks of time periods. And then with that reference frame shift, you can then display it as a function of height. So we're turning a time series into an altitude dimension. You do this a bunch of times, and you can fill out a nice time height parameter space with multiple UAS profiles of data. But as my favorite philosopher Spider-Man once said, with great power comes great responsibility. So with these measurements, we also need a way to characterize how accurate they are. And that's a very vague term. When most of us think of accuracy, we probably think of concepts like bias and imprecision and maybe even a dynamic error, like a time response or a time constant type error. I apologize to any OU students for this figure. Hopefully I'm not bringing up too much trauma for your measurements courses. But this is a really nice, concise way to look at this. There are also a lot of other considerations or error sources in atmospheric data, such as non-stationarity. These are things we can't change. We're subject to the diurnal cycle of the Earth's evolving state continually. There are systematic errors, which is an underestimation of the largest scales. That's kind of gross. And then there's also random errors, which is really what I'm going to be focusing on today. Random errors are due to an insufficient amount of averaging time to really be representative of the background flow. So these first three can typically be mitigated or at least reduced via calibration or design considerations for how you set up your experiment. But the others really end up as a trade-off in how you where you choose to sample, when you choose to sample, and how you post-process your data. So you can't always change the fact that the sun is going to come up and continually heat the boundary layer in the morning, unless you have some type of supervillain weapon, which then maybe we should talk after this because that'll be pretty cool. So really the theme of my talk moving forward today is going to be how do we quantify the representativeness of UAS observations specifically within the stable boundary layer. If you've come to any of my other talks, the importance of really getting our observations right in the stable boundary layer compared to the convective boundary layer is also of paramount importance. Specifically, we're curious in how these random errors change with stability and measurement height, how large they are for a typical UAS emulated profile, and then what does this mean for how we conduct our UAS operations? Should we really be thinking about some type of modulated ascent rate? So let's focus on what are even random errors. I'm sure this was kind of a brand new concept to me when Scott brought this project to me about a year or two ago. But really, if we start from the fact that in the atmospheric boundary layer, we are pretty much only using time averages in order to approximate our ensemble averages that all of our theories are really based off. There's no way to get an ensemble average of observations in the atmosphere unless you're Dr. Strange with infinite vision into the multiverse and can collect observations somehow like that. So we're really only left with the ability to collect time averages. And this is fine. With the ergodicity hypothesis, the time mean will eventually converge to the ensemble mean if we average for long enough. And then, therefore, that produces the contrary being true. If we do not average for long enough, we will be subject to random errors. And this can be visually represented here with some synthetic data provided by Scott. Pretend this is a random scalar flux, vertical flux, W prime C prime bar on the y-axis. And then on the x-axis here is the amount of time being averaged over. So each of these groups represents different bins of being average. And you can see that they all kind of spread around the true ensemble mean of 0.5. But as you increase your averaging time from tens of seconds up to thousands of seconds, we observe the spread in all of these individual averages will decrease as a sort of power law. And this is what we're really interested in here, what we're trying to take advantage of. So the standard deviation of the ensemble of the time averages will decrease as you increase your averaging time. So for a given, let's get a little bit more quantified here. For a given atmospheric parameter, we'll call it F. This can represent anything: velocity, temperature, or fluxes, or transport, or variances, or anything. We have an error variance for the ensemble, sigma squared, and that directly can be proportional, as shown by Lumley and Panofsky in 1964, to the actual variance, the ensemble variance of this parameter, divided by the number of independent samples. And an independent sample is related to this concept of an integral timescale, as well as an averaging period you're looking at. So intuitively, we see that for a larger integral timescale, we're going to have a larger error variance. Timescales are kind of like a memory in the atmosphere. So a process, the amount of time it takes an eddy to turn over is somewhat related to that. And if you average for a longer period, your ensemble error variance will also decrease. We're going to consider the aspect of relative random errors. So we're just going to normalize by the ensemble mean of that variable itself, so that we're working more with the percentage instead of a bunch of numbers with random units. So this is the definition of our relative random errors. That's just the square root of this divided by our ensemble mean. So this is fine and dandy as long as we're able to calculate this integral time or space length scale. And as it turns out, this isn't actually a very easy thing to do. So the definition of this, one of the most plain definitions, is just an integral from 0 to infinity of a function's or a process's autocorrelation function. That's rho of tau. And when you're working with, again, real atmospheric data, there is no infinity. We are not capable of integrating from the Big Bang to the heat death of the universe for a parameter to get the true autocorrelation length scale. So we need to choose some sort of upper bound that we integrate towards in order to converge our autocorrelation function to one explicit value of our length scale. There's a lot of different ways you can do this. You can choose the first zero crossing. Typically, this will decrease and then kind of oscillate around 0. Sometimes that's not actually the case, though. So you can also assume an exponential function to integrate analytically. You can fit some type of lag window with fancy signal processing and filtering. But at the end of the day, these are all choices that need to be made, and they all will give you a different answer, unfortunately. Moreover, within atmospheric observations, I've said this again, I'll keep saying it all day, we're limited by the diurnal cycle for stationarity. So you can't integrate for too long, or else your process is no longer stationary. And autocorrelation really only works as a concept when you have a stationary stochastic signal. Excuse me. So, wink, wink, it would be really nice if we could estimate random error without this a priori knowledge of the integral scale. And then, so along comes what we have is the relaxed filtering method. So again, let me define a given stationary stochastic signal, x. We can filter it at varying timescales, delta t. So this is the same concept. You can average it at increasingly long times or increasingly large distances. And it has been shown that this error variance of this filtered signal x tilde will decrease as a power law of a constant times the averaging time to the minus first. So Scott, Selesky et al. 2012 showed that you can take advantage of this power law in atmospheric data and fit a power law for a nice window of observations, which can then be extrapolated out to where you don't have substantial samples to actually estimate your random errors for any value of averaging time that you may desire. So we can again take this nice data where the power law is very strictly obeyed within a window that is well represented by the observations, and then extrapolate it out to your desired averaging time. And as it turns out, DS et al. 2018 showed that this exponent does not necessarily need to be fixed at 1 or -1. It can actually vary freely due to considerations for long-term persistence. And this concept works exactly the same, but now you're just fitting this constant and the exponent. Thankfully, Python makes that pretty easy to do with the SciPy curve fit tool. So this is the premise of how we're going to move forward. We're going to try to use this relaxed filtering method to estimate relative random errors for a whole bunch of different parameters within the stable boundary layer. And we did this by running a large suite of 6 different large eddy simulation experiments. This is pretty dense rundown of all of the different specifics here, but of note, we are making use of the Lagrangian average scale dependent dynamic model. This is a pretty big upgrade over a lot of other studies that have looked at the stable boundary layer turbulence, namely because we're able to really be confident in our subgrid physics schemes more so than other models like static Smogorinsky that are known to be overly dissipative close to the surface, which we're very interested in for our considerations here. Our domain is 800 by 800 by 400 meters. And we let this run for 10 hours, interpolating in the last 4 hours out to a final resolution of about 3 meters. And this is valid for geostrophic winds at 10 meters per second and a Coriolis parameter equal to up at about 65 north. So another thing to note is that in convective simulations with large eddy simulations, you typically prescribe your surface fluxes. Now, this doesn't really work in the stable boundary layer for a lot of math considerations that I'm not very fond of, but you can check out some recent papers by Jeremy Gibbs et al. To see why we instead prescribe a surface temperature to force a stable boundary layer through these simulations. So this is the main parameter that is changed for all of the different simulations. And here is kind of a grid of the different parameter space we looked at. So we have 6 runs, A through F, with increasing stability. We increase our cooling rate from 0.25 Kelvin per hour all the way up to 2.5 Kelvin per hour. So this is going from, this really results in a nearly weakly stable to nearly neutral regime, all the way up to a very stable regime that you might only see somewhere close to the South Pole in Antarctica. So this provides a really wide parameter space of a stable boundary layer. And these parameter spaces are based entirely on the Huang and Buzi 2013 paper, since we're also using the same code that they utilize. So we're basically doing the same thing here, except for finer grid spacing and completely different use of the final products. Our stable boundary layer depth, H, spans about a factor of 2 when it's all said and done across these stabilities. We define, again, we all know the boundary layer depth is hard enough to determine in the convective boundary layer. So how the heck do you even do that in the stable boundary layer? Well, common method among people in LES with stable boundary layer simulations is to extrapolate where our Reynolds stress profile linearly reaches 0. So this gives us confidence that all of the turbulence is relatively contained within the stable boundary layer. This is different than other techniques of finding the maximum potential temperature gradient or other types of minimum fluxes or something. But this does enable us to fully contain the low-level jet core within the stable boundary layer as well, which we think is an important feature. So all of our statistics and all of our figures will be normalized by the stable boundary layer depth H. And we can also see our mean lapse rates increase by about in order of magnitude from the weakly stable to the strongly stable cases. So why don't we go ahead and jump right in to our random error profiles, mainly the first order. This is not Kylo Ren's first order, but sometimes it feels like Kylo Ren is force choking my code. But here is plots of relative random errors for wind speed, wind direction, and potential temperature plots across A through F. And you will also be curious to know that we have chosen an averaging period of 3 seconds. And this is very intentional. We are trying to see what type of typical framework in post-processing UAS data, specifically what the errors will look like. So usually, at least in the stable boundary layer, for example, my recently accepted paper in boundary layer meteorology out in Finland, we were ascending at 1 meter per second and averaging to 3 meter grid bends. So that means we were averaging over 3 second intervals. We will talk more about this implication of the averaging time in a couple of slides. But we can see that as we increase in stability, our wind errors generally decrease, both wind speed and in wind direction. However, our potential temperature errors increase with stability. And this can be explained somewhat physically through the idea that for the higher stabilities, we have a more rapidly changing temperature profile at the surface. And low down near the surface, this is this temporally changing potential temperature gradient is actually a source term for potential temperature variance, if anyone wants to dig into their boundary layer notes, or if Scott hasn't gotten there yet, probably. So if we have a larger variance near the surface, that means you need to average over a longer period in order to more representatively, that's maybe a word, more accurately represent the background average temperature. So kind of a roundabout way to explain that, but I think that all checks out physically. It is good to see that all of our errors do decrease with height. This kind of makes sense. As you get away from the surface, you're less impacted by it, even though stability in the stable boundary layer, that's not as much of a concern as you end up with Z-less stratification as well. But this may also be related to our wind speed profiles increasing with height and potential temperature increasing with height as well, since again, these are normalized profiles. So for the sake of brevity, I will not show the second order profiles, but you can rest assured that these types of patterns are fairly similarly represented in these moments. So a quick recap, going back to question 1, how do our random errors depend on stability and height? Well, all of our errors decrease with height, whereas the wind errors decrease with stability, potential temperature errors increase with stability. So how can we take this another step further and apply it to what we would actually be measuring in the stable boundary layer with a UAS? So fortunately, having the volumetric output from large eddy simulations is extremely powerful. We can then emulate exactly what a UAS might see without any effects from measurement bias or imprecision or any of those other types of things. So we output a virtual tower in the middle of the domain. So that's outputting a time series at the 0.02 seconds. So however many hertz that is, basically sonic anemometer data at each grid point level in the center of the domain is output as a separate time series file. So we're able to then subsample what it would look like as a UAS ascends through the continually evolving atmosphere. And this is UAS profiles are quasi-instantaneous, but they're not literally instantaneous. We're not shooting a light beam or sitting at a fixed position continually. So the atmosphere does evolve. It takes about 3 minutes in this case to ascend all the way up through the full boundary layer depth. So moving on, we're going to assume a 1 meter per second ascent rate with 3 second averaging time, resulting in 3 meter altitude bins. From this subsampled virtual tower data, and to be pretty much exactly consistent with data from the Isobar 2018 campaign. And what I'm going to show you next is basically the result of what happens when you process those data in the same exact way that you would from regular UAS data. So here we have from case A, the weakly stable profile. Shaded in green or contoured in green is what is observed by the UAS just directly with averages in those bins, compared with the black lines being the ensemble average or the LES temporally and spatially averaged profiles is what we're really trying to represent as the true background flow. And then shaded in green in the same color represents 1 and 3 sigma, respectively, of the relative random errors at each height for each of these different parameters. So right away, we can see that the mean or the UAS profile does a decent job approximating the mean profiles in the first place. I mean, there's definitely some wiggles, as to be expected. This is what raw data profiles look like anyways. But when you factor in the shading from the relative random errors, they're not relative anymore. These are actual physical random errors denoted on here. We see that we fully capture the ensemble mean at all heights for all of these parameters. And that's a really powerful tool here. Now we're able to characterize really the representativeness of these different measurements. It means a lot more to have confidence bounds or error bounds on a single profile. And you'll also notice that these errors near the surface are quite large, especially in wind direction. This kind of sucks. This is almost a 90-degree, if not more, of a range near the surface when you're only averaging for 3 seconds. But if anything, this really shows the utility of the synergy between UAS and other ground-based systems like any covariance tower or a Doppler wind LiDAR that's able to have some type of scanning strategy to retrieve low-level winds. But because of these errors, it's pretty difficult to constrain them. And we'll, again, look at more of this in a couple of slides. Then really quickly, looking all the way at the end of the spectrum, at the very stable case for case F, the raw UAS profile looks pretty darn good to begin with, but the context of this shading really makes a big difference, again, with these large errors near the surface. So how large are our errors in UAS measurements? Well, it turns out the profiles are fairly comparable to the ensemble means to begin with, but these error bounds are really helpful for contextualizing the individual profiles. Whew, excuse me. And since the errors are so large near the surface, it might make sense to then couple with some additional observations. And let's put that into some more context. So here I'm showing a wider parameter space than I have been so far for these UAS measurements. So let me orient you here really quickly. We have wind speed, wind direction, and potential temperature in the columns, and then case A and case F shaded on the first and second rows. And then shaded here, we have the potential, the relative random errors as a function of height and averaging time. So maybe if, if we're on the cusp of that 10% error, maybe if we were just to average for a couple seconds more, that's kind of fine operationally. Might as well do that. How does that change the types of patterns we see? Well, unfortunately, these errors below Z over H equals 0.1 are still pretty difficult to constrain. So errors near the surface, for reference, remember that H was about anywhere between 1 to 200-ish meters. So 0.1, we're looking at about 10 to 20 meters near the surface. So right exactly in the Goldilocks area where a tower could be measuring for some backup. But we already have enough issues with constraining our measurements from UAS in that area anyways. But we see, no matter how long you're averaging for, you're still right around that 10% error in wind speed, all the way up to 15 seconds of averaging time. Then you're ascending at ridiculously slow speeds. Same issues with our wind direction. Potential temperature in the near neutral case doesn't really change a whole lot with height or with averaging time, since the errors were so small to begin with. We're looking at 0.05% relative random errors maybe. So we're looking at maybe an order of magnitude less than the calibration errors for a thermistor. But as we increase in our stability, this becomes a much bigger concern. Our errors increase drastically if we were to decrease that averaging time, and even doubling and tripling our averaging time doesn't do us a whole lot of good in terms of our absolute errors, which are anywhere between 1/4 and 1/2 of a degree Celsius, which is you're butting right up against your calibration errors, which are separate from one another. I don't know if I've made a good enough emphasis on this. When you have these relative random errors, they are in addition to any other uncertainties that you may have. So if you have a plus or minus 5 Kelvin temperature calibration, and then you have a plus or minus 0.5 degree random error, then you're looking at almost a full degree Celsius that are may or maybe not added linearly, but these are really important considerations to remember. So in order to continually going down this rabbit hole of, okay, how can we better optimize our UAS sampling strategies, we can actually then back out or do some reverse some of the math to calculate some optimal ascent rates for measuring our different parameters. Here, I'm just going to zoom in on wind speed. So again, here's weakly stable and very stable for cases A and F. And then if you reverse the problem, and if we assume that we want to be able to have our 3-meter bins, then we need to figure out, well, how long do we need to average within those 3-meter bins? And then you can then look at what your ascent rate ideally would look like. So for a given error level. Sorry, this is kind of a roundabout way to explain it, but let me try again. If you want a certain level of error, then that means you need to average for a certain amount of time. Since we're continually ascending through the SBL with the UAS, ideally, the way you can modify your averaging times could be to modify how fast you ascend. So go up slower for longer time and vice versa. And we can see that as we specify lower and lower errors, we're really shooting ourselves in the foot because we need to ascend much, much slower. So I've drawn this gray line to show 1 meter per second. And for context, I've also shown this red dashed line that represents the minimum ascent rate. If you were to hold everything constant and minimally ascend at that constant rate, how high can you get all the way up to z equals h within a 15-minute window, which if we had the OU copter sonde, that would give us just enough time to come back down and land safely with 1 full battery charge. So you can see that a lot of these curves are living on the wrong side of that dashed red line. And at some point, the operator and the end user is going to have to make some tough decisions on, do I want to be able to ascend all the way through the atmosphere? Or do I want to really nail down the errors low down close to the surface? And these decisions can be made easier depending on what other observations are made readily available, like towers, mobile mesonettes, other UAS, other types of instruments, whatever that may be. So you could probably stare at this figure all day and think about it in all different ways to plot this. I know I have, but for the sake of time, I'll wrap up this section by saying we definitely don't really necessarily want to be flying at constant rates. I know that, at least in my experience, an ascent rate for UAS is pretty much chosen as a balance between a sensor response time, the maximum altitude you want to achieve, and the amount of battery you're capable of your payload is able to use, with very little thought to the notion of these relative random errors. So I think this is something we really need to think about moving forwards. And we also have studies looking at the convective boundary layer, which I know will perk a lot of y'all's ears up as well, currently underway in this same framework. So to kind of wrap all of this up, we simulated 6 different cases with large eddy simulations. We adapted the relaxed filter method for use from tower data in time series format to spatial data in large eddy simulation volumetric output. This is all in an effort to really quantify the representativeness of individual UAS profiles. Some of our results included the fact that our wind speed and direction errors decrease with height and stability. However, potential temperature will increase with stability. We saw that these error bounds on emulated UAS profiles really add a lot of confidence in the ability of profiles to represent the ensemble mean. And with enough trickery and enough knob turning, we can determine some optimal UAS ascent rates for a given desired error level. And then this induces a big, larger scale discussion that I open to the community welcomely of how do we choose the different trade-offs between errors and perhaps maximum flight levels. So this can also be applied to the convective boundary layer. And I do have a bunch of extra slides for what the second order profiles look like. for advanced UAS sampling strategies or an infinitely tall tower throughout the depth of the boundary layer. A lot of similar cases can be made for all of these results as well. I know that I have thrown around the idea of flying multiple UAS at once so that you can average those together to maybe increase the spatial representativeness. In my isobar paper that was recently accepted, we averaged subsequent profiles after one another to improve representativeness. As of now, I don't have a good say on how those might affect relative errors or random errors, because then you get into the weeds of some weird signal processing considerations, and we will definitely need to think about that moving forwards. But anything to make our UAS measurements better and more useful for our friends in research land and operational frameworks is really the name of the game. So with that, I'll go ahead and leave up this conclusion slide and say thank you all for coming. I know that there is a colloquium afterwards, so definitely don't ask me any questions. Let's go. No, I'm kidding. Thank y'all. Okie doke.
Okay, so regarding your research showing that there was lower errors higher up in altitude, but higher errors lower in altitude, would you say that would mean that for the copter sonde, it would be best to use slower ascent rates closer to the surface, but then past a certain height, use faster ascent rates?
Yeah, that's really what these results are showing. And that's a really tough, like I said, that produces such a trade-off of how slow do you go. If you go too slow, then you can't get up high enough on a full battery charge.
Right.
And you know, I know that the copper sonde is capable of programming such missions. Tony brags about that at least, so I can put his money to his actions, I guess. But yes, to answer your question.
Was there found a cutoff height beyond which you could increase the UAV ascent rate where the errors were less?
Yeah, let me try to go real quick. Let me go back a couple slides to this ascent rate. So somewhere in the middle of the boundary layer, depending on what your acceptable, tolerable threshold for errors might be, somewhere in the middle of the boundary layer, you can make up for lost ground potentially by increasing your ascent rate. I know the copper sonde, I extended this all the way out to 10 meters per second. That's kind of an absurd ascent rate. I think the copper sonde can do that, but definitely not for very long. So
around like 1 to 2 kilometers, perhaps.
Oh no, we're not even looking that high. So remember, the stable boundary layer in these cases were a couple hundred meters. So because we're ascending so slowly to begin with, that's why these parameters kind of look the way they do. But in the convective boundary layer, that's going to be even trickier. I don't know what those results are going to look like, but when we have 5,000 feet to contend with, it's going to be tough.
So it really depends on the configuration and of the stable boundary layer for the height with which you increase the UAV ascent.
Absolutely. So yeah, really long-term follow-up studies from this could include expanding that parameter space of stabilities and domain sizes and topography and all that good stuff, so that an end user could like kind of punch in some numbers for a back of the envelope calculation based on input parameters of, hey, it was roughly this type of inversion we saw, lapse rates near the surface look like this, we had this ambient flow, etc. So yes, great questions.
Thank you.
Mm-hmm.
Hi, Brian. This is Qingyu.
I
think this is really a great talk, and this is really informative. I think my question would be really basic. So I feel like for measurement for wind, for example, wind speed and wind direction, it is more, it is larger relative error near the surface. I understand that because the turbulence is happening and that associated surface condition, etc. But for theta, potential temperature, I feel like the potential temperature relative error is larger when the altitude increase. I don't know why it has caused it. Is that associated to humidity? But humidity is more changing swiftly near the surface too. So what has caused that?
Yeah, so thank you. Great question. And it all relates back kind of to this concept of the integral length scales or the integral time scales, which are the whole purpose of this technique is to avoid having to measure those because they're not always necessarily defined within a given flow. So you can make the physical arguments based on these results, but also keep in mind that that may or may not just be hogwash. But anyways, my answer to that would be because, yeah, your potential temperature length scales are going to be larger near the surface for higher stability because of that continual cooling that's going on. So you have lots of rapid changes relative to maybe a weakly stable boundary layer. So you need to sample over longer durations or over longer distances to constrain those. And as for, I think I'm going off on a tangent. Why do they decrease with height then? You're getting farther away from that primary source of cooling near the surface. So your potential temperature variance kind of decreases with height in general, at least a little bit. And your length scales are somewhat more constant with height. So I have some figures to show you that I could walk you through with what I'm thinking through here. If you'd like to chat sometime offline.
Okay, thank you very much. That's nice answer there.
Thank you. Is the efficiency of UAS batteries expected to increase in the near future? Boy, I hope so. Honestly, Tyler Bell might be able to answer this better. I don't know if Tony's on here. Or Liz, you might be able to as well. But theoretically, yes, batteries are getting denser and denser and payloads are getting smarter and smarter. But at least with the current technology and the physics of rotary wing UAS, we might be stuck to the 15 to 25 minute, at least for the Coptersond, 15 to 25 minute endurance profile for a long time. There are other private companies out there that have batteries the size of a small child that will give you an hour of flight time with the rotary wing UAS. But then you have a big battery, lots of heat, lots of weight, a lot less maneuverable, a lot more susceptible to wind fluctuations, or maybe less susceptible to wind fluctuations. So it's a lot of gives and takes and pushes and pulls with what type of UAS you're trying to create. But fixed wing UAS, on the other hand, they can have flight times on the order of hours, just because they make use of being able to glide around, especially these really nice turbulence sensing packages with these really long gliders that have like a 6 meter or 3 meter wingspan. They can fly around and just drift around forever. So it really depends on what type of problem you're trying to solve. But at least for the Coptersond, I assume that companies have much incentive to keep improving their technology. We're really at the whim of private companies at this point. Let's see. Vivek also says, have there been any indications of how fog or mist in the stable boundary layer affects the response time of sensors on the UAV Coptersond? Would fog or mist require a slower ascent rate of the Coptersond? That is a spectacular question. And we really only flown in fog or mist kind of by accident, during isobar. We're technically not allowed to fly in fog in the US. But my idea would be that you start messing with the physics of how these different sensors work, especially like your relative humidity sensors are this type of really thin membranes that are really, once you get them wet or have condensation on them, you kind of ruin their permeability long term. So you will eventually increase your errors with time using the same platform. But with regards to response times on sensors, I'm not entirely sure. Scott, you might be able to speak more on that if you're still here, since you're doing your cloud chamber measurements with Kendra, but I'm not entirely sure how. I'd have to think about that for a little bit. So go ahead and send me an email maybe, and we can think about that some more, Vivek. Yes, Liz, excellent point. When it's cold out, these batteries also drain so much faster. They don't want it. They want to exist even less than you or I standing out in the Arctic Circle during winter. Mhm.
I have one real quick. So you've looked at things, kind of as a function of stability here in relation to the stable boundary layer. And you're kind of motivated by looking at the turbulence and how that affects things, right?
Yeah.
So relative to how much, how do I phrase this? This is difficult to phrase. Because I'm thinking of extending, what you're thinking or you're already thinking it to the convective boundary layer, but how would you expect your relative errors to scale, based off, say, take wind speed, for example.
Yeah.
Is it really the turbulence itself that is causing the most error, or do you think it's just the wind speed by itself? So like I've looked at all this stuff compared to the LiDAR, and I can see pretty clear signals. Basically, it's what you've looked at as well. But I'm not resolving those same scales that you are. So do you think it's more of the turbulence doing it, or do you think it's just the inherent inability to do it based off of the physics of the craft, I guess?
I think I get what you're saying, and these results are somewhat deceptive too, right? Because the errors scale with the mean. So when you have low wind speeds near the surface that are already really light and variable and intermittent potentially, you're dividing by a smaller number, so you get bigger errors. Like, good job, Brian. But in reality, we do have to contend with the fact that it's really difficult to measure wind speeds at such low velocities, regardless of your sensing platform. I mean, even eddy covariance sonic anemometers don't do a great job at slow wind speeds. So I think the answer is both. A 10% error does mean a lot more when your wind speed is only 1 meter per second too, right? So it's important for it is related to the turbulence, because you might be getting some type of near surface or ejection or sweeping motions from potentially large scale motions, is where you could take that conversation as well. Wink, wink, where the rest of my dissertation is going. In the convective boundary layer, honestly, I would bet you see similar issues near the surface. I bet errors would be large near the surface, because you still do expect that logarithmic profile where your velocity vanishes towards zero. So maybe there might be a better way to define errors in wind speed and direction in this type of framework. But to answer your question, I think it is a little bit from column A and a little bit from column B. That's fair.
And have you had a chance to go back and see if you see any of these same effects in the actual observations from isobar or any of the other weakly stable stuff we've done, like in lapse rate?
That would be a really cool study, wouldn't it? Is taking the time series data and seeing how well the raw data approximate the 30 or 60-minute averages. Yeah, no, that would be really cool from towers. So no, I have not. This is the tip of a very deep iceberg, intentionally.
Yeah, I'm about to push it off the ledge.
Yes, please. I can't swim. Yeah. Thank y'all. See you later.